The law of conditional probability brings us to another law, which is the law of total probability. And the law of total probability basically gives us a way to calculate the probability of an event A, which sometimes it is hard to compute directly. And again, it is very easy to explain it with a Venn diagram. Suppose we have a sample space omega, and in that sample space we have three events, A1, A2, and 3, represented by those three squares. And suppose, as illustrated here, these three events are mutually exclusive and they are collectively exhaustive. Mutually exclusive means that they cannot both occur at the same time. A flipping coin can either result in head or tail, but not both. In our example, A1 and A2 cannot occur simultaneously. Collectively exhaustive means that at least one of the events must occur. For example, when rolling a die, the events 1, 2, 3, 4, 5, and 6 are collectively exhaustive because they span the entire range of possible outcomes. In our example, at least one of the events, A1, A2, and A3, must occur. If the A's are not exhaustive, then some parts of the sample space are missed, and thus we might miss some parts. Now suppose we have another event B in this sample space represented by the ellipse. B is made up of the intersection with A1, A2, and A3. B equals to the union of the intersection with A1, A2, and A3. And that would be true for any event B, whatever B happens to be, since A1, 2, and 3 span the entire sample space. If B looked something like this, for example, then B is made up of the intersection of B and A2 and B and A3, and the intersection of B and A1 is the empty set. We can also write it as the probability of B equals to the probability of B given A1 times the probability of A1 plus the probability of B given A2 times the probability of A2 plus the probability of B given A3 times the probability of A3. And again, the probability of A1 union A2 union A3 equals 1. Let's give a concrete example. We have a factory with 3 machines in it. 50% of the parts produced in the factory are made by machine 1, 30% by machine 2, and 20% by machine 3. Of the parts machine 1 makes, 8% are defective. For machine 2, 20% of the parts are defective, and it's 12% for machine 3. Suppose a part is randomly selected and we want to know what is the probability that this part is defective. What information are we given? If a part is randomly selected, the probability it came from machine 1 is 50% or 0.5. The probability it came from machine 2 is 30% or 0.3, and the probability it came from machine 3 is 20% or 0.2. Therefore, the probability of M1, meaning the probability that the part came from machine 1, equals 0.5, and P of M2 equals 0.3, and P of M3 equals 0.2. Note that these are mutually exclusive events that cover the entire sample space. The randomly selected part will come from one and only one of these machines. What is a conditional probability? What is a probability that a part is defective given it came from machine 1? According to the question, it is 8% or 0.08. And P defective given M2 is 0.2 or 20%. And P defective given M3 is 0.12. The question is, let's say that an event D is a randomly selected part is defective. What is the probability of D? For that, we will apply the rule of total probability. The probability that a part is defective equals to the sum of the probability it's defective given it was produced in machine 1 times the probability it was selected for machine 1 plus the probability it's defective given it was produced in machine 2 times the probability it was selected for machine 2 plus the probability it was defective given it was produced in machine 3 times the probability that it was selected for machine 3. So what we have is 0.08 times 0.5 plus 0.3 times 0.2 plus 0.2 times 0.12. We can also see it using a tree diagram. So we have three options for the machines, M1, M2, and M3. And for each machine, the part can be either defective or not defective. So if we are interested in the intersection of M1 and D, what we are doing is multiply 0.08 times 0.5. In the next unit, we will see how Bayes' theorem ties into this and how we can apply it to solve localization problems.